Good day, everyone, and welcome to the Water Research Foundation webcast, Implementing Machine Learning Process Controls at Water Resource Recovery Facilities. My name is Jeff Muller, and I'm a Director of Research Services at the Water Research Foundation, and I'll be serving as a co-moderator today, along with Dr. Nancy Love from the University of Michigan. I'll briefly go over a few housekeeping items as well as the agenda for today's webcast, and then we'll dive into our program. Today's webcast is scheduled to be 90 minutes, and that includes our Q&A session, which will be at the very end. In terms of housekeeping, please submit questions through the question box at any time during our webcast today. We'll do a Q&A at the end of all the presentations, so please keep your questions coming throughout the webcast. Slides and a recording of the webcast will be available at WRRF.org. You can download the slides now and access a link to the project page under the event resources at the bottom left of your screen. So those resources are available to you now. A certificate of completion will be automatically generated after the webcast. If you have any questions about that, please contact Michelle Suazo at the email shown on your screen there. And lastly, we encourage you to stay on until the end of the webcast to fill out a quick survey with your feedback on the webcast. Here's our agenda for today, and I will kick things off with an overview of WRRF Project 5141, which is focused on data-driven process controls and really forms the basis of the information that will be presented on today's webcast. I will be followed by Kate Newhart from Oregon State University, who's going to present on machine learning terminology and overview, including an overview of a machine learning framework that was developed by the project, which lays out the steps involved in implementation of machine learning. Kate will be followed by Joe Liebig from the University of Michigan, and Joe will give an overview of a machine learning toolkit, which was produced by this project team as part of this project, and specifically to help wastewater process engineers and other wastewater professionals to increase their understanding of machine learning, as well as to increase their understanding of implementation of data-driven process controls. So this machine learning toolkit was actually just published by WRRF. We haven't even really started to promote it yet. So this is, you all are the first to hear about it. This is hot off the press today. And then Joe will be followed by 3 case studies that will illustrate the steps involved in implementing machine learning at 3 different utilities. A case study on a biological nutrient removal presented by Jeff Sparks at HRSD, Hampton Roads Sanitation District. A case study on phosphorus recovery presented by Rudy Maltos from Metro Water Recovery and Joe Liebig from University of Michigan. And then a case study on holistic biosolids optimization presented by Nam No. And then that will be followed by a Q&A session at the very end. Here's a look at today's presenters along with their contact information if you would like to reach out to any of them following the webcast. In addition to myself, I'm joined by Dr. Kate Newhart, an assistant professor at Oregon State University, as well as Joe Liebig, PhD candidate at the University of Michigan. Our 3 case study presenters include Dr. Jeff Sparks, who's the Director of Digital Water at Hampton Roads Sanitation District, Dr. Rudy Maltos, a staff engineer at Metro Water Recovery, and Dr. Nam No, a research program manager at DC Water. And then Dr. Nancy Love, a professor at University of Michigan, will be co-facilitating the Q&A session at the end of our broadcast today. And if you'd like to read more about any of these folks, you can find that out on the bios tab to read their full bios for our presenters today. Okay, without further ado, I'd like to kick off with an overview of WRRF Project 5141, which is titled Data-Driven Process Control for Maximizing Resource Efficiency. And so this is a DOE grant-funded project that's being managed by WRRF. On your screen here, you can see the members of this project team. It's a pretty large project team. In addition to WRRF, it includes 3 utilities, which are serving as host utilities for implementation of the machine learning process controls. that are being demonstrated at full scale. And those utilities are HRSD, Hampton Roads Sanitation District, DC Water, and Metro Water Recovery. They're joined by 4 universities, which are supporting the implementation of the machine learning controls, including Oregon State University, University of Michigan, Northwestern University, and then University of Laval in Canada. And then we have 1 DOE lab, Oak Ridge National Laboratory, as well as a consulting firm, Black & Veatch, joining our team. For the project, we also have a utility advisory committee, which consists of the 9 utilities that you see on your screen there that are providing end user input and feedback to the project. It's a relatively geographically diverse group of utilities, as you can see from the map there. And we're just really grateful for their participation and feedback throughout the course of the project. So a little bit about the background or rationale, or why are we doing this project? As many of you might be aware, water and wastewater treatment facilities consume a significant amount of energy, and in fact, 3% of all U.S. energy. However, currently most water resource recovery facilities use 20th century controls for monitoring and controlling their systems. And these often require large design safety factors. However, many utilities, maybe most utilities, are producing and collecting a large enriched data stream, which is often underutilized. So machine learning controls provide new ways to synthesize, analyze, and model the data that's being collected by utilities. In particular, machine learning controls using that data provide the opportunity to reduce costs, reduce footprint, increase capacity, reduce energy and chemical use such as methanol or polymer or disinfectants, increase energy and nutrient recovery like phosphorus, as well as improve environmental performance, for example, reducing greenhouse gas emissions, improving water quality, or improving process reliability. So essentially, these machine learning controls provide an opportunity to intensify our treatment processes, as well as an opportunity, I would say, to do more with less in shorter words. So for our project, we have 2 primary objectives. First is to develop and demonstrate data-driven process controls in real full-scale facilities for 5 promising applications. And by applications, I mean process technologies, innovative process technologies that collectively provide a whole plant approach and offer substantial energy and resource recovery benefits. And then second, to create a machine learning toolkit of new process control approaches, along with an implementation guide to help other utilities on their machine learning implementation journeys. So for the 5 promising applications, you can see those on the screen here. It includes carbon diversion, high rate contact stabilization, which is being implemented at DC Water, biological nutrient removal, ammonia-based aeration control, and ammonia versus NOx plus partial denitrification anammox. That's a long list of acronyms there, which is being demonstrated at Hampton Roads Sanitation District. Disinfection using peracetic acid, which is not widely used currently in the wastewater industry, and that's being demonstrated at Metro Water Recovery. And then phosphorus recovery using a MagPrex system, also at Metro Water Recovery, which hosts the largest and I believe first MagPrex facility in North America. That picture you see in your bottom right is a picture of the project team standing underneath the MagPrex reactor at Metro Water Recovery. And then lastly, holistic biosolids optimization, which is being demonstrated at DC Water. This diagram here is an example plant schematic showing the application locations. So the sewage is coming in at the top left of your screen there. So you can see the application number 1, carbon diversion, located near the primary treatment. Application 2, BNR, downstream of that. Application 3, disinfection, further downstream of that in the liquid treatment stream. And then applications 4 and 5, phosphorus recovery and holistic biosolids optimization, are located in the solid stream. So, visually, if you look at this, you can see this is kind of collectively providing a whole of plant approach. You can really apply machine learning controls just about anywhere in your treatment process. And in terms of the project status, we started this project in October of 2021. It's a 4-year project, so we're nearing completion now, about 95% complete. As I mentioned before, the machine learning toolkit has been published. We have a draft final report, which is currently under review and will be published in just a couple of months. So be on the lookout for that when it comes out. And then our total project budget is about $2.2 million, with about half of those coming from DOE funds and the other half coming through cost share from the project team members. And so now I'd like to hand it off to Dr. Kate Newhart to cover our next presentation. Kate.
Thank you, Jeff. And I'm happy to be here to talk about what does machine learning look like in the water sector, and what are some important terms that you need to understand when you are shaping your own machine learning problem. So today we'll talk broadly, what is AI, right? AI is a computer system, so a set of algorithms that can perform tasks that we have typically or historically associated with requiring human intelligence to achieve, right? So image recognition, right? So parsing out those CAPTCHAs or detecting a vehicle, right? That's a perception task that we assume a human would need to be able to achieve, or, right, the recommendation engine from Netflix or fraud detection in your bank are examples of reasoning and decision-making that we associate with human intelligence. But what I want to emphasize here is that what AI does is it mimics decision-making. It's mimicking perception using these sets of algorithms. So when we say learning, it's not the same learning that you or I use, but it's learning in a mathematical sense. And today we're specifically going to be talking about a subset of artificial intelligence called machine learning. There's a host of different AI applications. So if we talk about ChatGPT or other large language models, that falls under natural language processing. If you talk about the image recognition, right, that's computer vision. And so machine learning specifically, or ML, uses an algorithm to infer how to do a specific task without explicit instruction from the data. So if you have fit a linear regression model in Excel, you have done supervised learning. So what I mean by that is supervised learning means you have given the model an explicit output. So there is a data point, you have a number or a classification, and the model's job is to mimic the relationships between your inputs and your outputs. When you do not have an explicit output, that's an example of unsupervised learning. And that can be used for clustering of data, right? Say you have a bunch of microbial data and you want to see those similarities, or you're looking at fault detection, something that's in or out of control. And then finally, reinforcement learning is another flavor of machine learning, and that involves the model making decisions based on how it can interface with the environment. I will say that supervised learning and unsupervised learning, we need to really get our heads around that as an industry and how it can work with our data before we can really push reinforcement learning. But that would be one of the next big advantages and movements forward, both for the technology and for our industry. So I'm going to talk now a little about the similarities and the differences between fitting a statistical model and a machine learning model. So for example, if you were to collect some data, right, you would export that data and organize it into a machine. So most commonly using Excel, and you would select a model type, in this case, a linear regression, to fit the model. A linear regression has two model parameters, so the slope and the intercept highlighted there. And what Excel does is it actually iterates through different combinations of slopes and intercepts in order to give you the lowest error, right? That is your model. That's how most of us do it. Now, when we go to machine learning, It's a little bit different. So let's start on the right-hand side there with our model. So that visualization there is an example of a neural network, which is a very complex machine learning model, but it's very flexible. Now, each one of those lines and each one of those nodes have multiple model parameters associated with them. So even a simple machine learning model can have over 100 parameters, and a more standard machine learning model can have over 1,000 internal model parameters. So to fit all of those, we now have to get outside of Excel and start looking at tools like Python or R to do this job. And if we take a step back and think about, well, how much data do you usually need to fit a linear regression with just 2 model parameters? Now increase those number of model parameters to the hundreds of thousands. Well, that's why we need not just a lot more data, but a lot more diverse data. So let's talk about another way that machine learning is different by walking through an example where we can talk about contaminant removal with a chemical. So let's say you go to your bench, you do a bunch of experiments, and you visualize that data, and it looks like there's a linear relationship between the chemical dose you apply and the removal. So you fit that, the data looks pretty evenly distributed across that range. Great, you have just fit a statistical model. Now, let's say you know that your chemical it has pH-dependent speciation at the range you're concerned about. Maybe you know some chemical equilibrium or precipitation modeling. So if you're incorporating physics, chemistry, biology, we call that mechanistic modeling. But let's say your data looks something like this, and you don't have enough information, right, using just the dose and response information to fit your model. Well, what if you were to include other process information, so other water quality variables that you're collecting at the same time of your samples, and you now use a very flexible model structure to connect all of those inputs to your output? That's an example of using machine learning. Now, there's some specific implications when we use these 3 different model types. So when we fit a statistical model, we have analytical uncertainty estimates. So those are our confidence intervals, very important in engineering design. When we use a mechanistic model, each of those internal model parameters have physical meaning. So whether that is comparing them across different systems, looking at them over time, or just getting a reality check, that physical meaning is very important for operations. But machine learning doesn't have either of those properties. Now, we can experimentally get a confidence interval, but it's not an intrinsic property. And there is no physical meaning of all of those internal hundreds of thousands of model parameters. But instead, when we are not pathway dependent, so understanding the inner workings, we can answer different types of questions with this incredibly flexible model structure. So this is the framework that we used on this DOE project for our machine learning model. And I'm going to talk through some of the nuances of each of these points as we go forward through our project, starting with defining the problem. So there's a few different ways you can use machine learning. The simple is regression, so predicting a numeric value. The second is classification, so predicting high or low, in control or out of control. So not a numeric value, but a class or a grouping. And then there's another type of model, an optimization model. So an optimization requires that you have your regression model or you have your classification model. And then there's a second model that operates around it to modify, right, maybe your energy inputs or your cost or your chemical inputs in order to achieve the same output. So optimization has a very specific meaning in both how you apply and how you use machine learning. So just be careful with how you use it. What types of problems can we use in the water sector for machine learning? There's 2 terms that I want to talk through. So first is soft sensor. So we're all very familiar with a hardware sensor, right? So there's an example of an ammonia sensor there on the left. But let's say maybe you needed an ammonia sensor in a different location. Well, if you were to build a machine learning model of that ammonia, right, using other variables and other locations throughout the site, that would be an example of a soft sensor. And soft sensors can easily be used in control and monitoring strategies, very similar to how existing facilities are using them today. Another term that's important to understand for our sector is what's called a digital twin. Now, this definition of digital twin here has been widely accepted for our sector, and that is that it's a model of a physical entity like a blower or a pump with an automated bidirectional live data connection, right, to this model, right? So this model is receiving data from your physical entity, from your blower. You are updating the model, you are running an optimization, and then you are sending that information back to the blower. And you allow that model, which often will include both a mechanistic or physical component and a data-driven component, is allowed to evolve over time. So digital twins, I will say, relatively easy to do for an individual piece of equipment. And the big dream is that we can move towards the facility-wide digital twin. But as you can imagine, that gets a lot more complicated. And then finally, I just want to touch on what makes a good machine learning problem. Please do not be a hammer looking for a nail. So don't walk around thinking, oh, I want to use machine learning. Let's see where we can use it. Rather, ask yourself some of these questions and then see if machine learning is a good question or a good answer for your specific problem. So first off, make sure that your problem statement is specific to an objective that matches with the properties of machine learning. So like we discussed earlier, machine learning doesn't have any physical meaning to those internal parameters. That is an active area of research. So if your objective is to understand the chemical kinetics of that little dose response exercise we talked about earlier, then a mechanistic model or a statistical model is much more useful to answer that question. But if you're looking at a precise prediction and optimizing energy kinetics, then maybe machine learning is a good answer. The next is your model, a simpler model has already been attempted and it cannot capture the observed trends. So you can obviously recognize a trend with sufficient accuracy. So it's important to say, this is the amount of accuracy my model needs in order to be successful at this phase. And then finally, making sure that you have enough data, not just throughout the sampling campaign that you use for this particular project, but much larger, you have the resources to continue to collect that data if it is deemed necessary. Because as the conditions change, you want your model to adapt with it. All right, now that you've defined your problem, we can talk about getting the data. So I'm going to talk a little bit about the terminology here. So computer scientists and statisticians use slightly different terminology than engineers, but for the most part, they can be used synonymously. So while we talk about organizing our data as variables and rows, statisticians will often refer to them as features and observations. And the same goes for model inputs and outputs. They talk about them as predictor variables or predictor features and response features. When you are organizing all of your data, it's often that I hear, oh, I have so much data. But you really have to think about what is your lowest common denominator. So do you have sensors that are frequently down? You might have gaps in the time that you have, or it's not well calibrated. If you're using lab data, so that example on the top there is a sensor, and the example on the bottom is a lab data, you'll see you lose about 60% of the data that you think you have when you have to reduce everything down. So water sector data really isn't the big data of the Googles of the world. So we actually have a bit more of a challenge. And it's not just the quantity, but the quality of data. So if you've been operating your system at the exact same dose for the last year, or maybe small adjustments, that is all your model is going to be able to predict if you use machine learning. Machine learning cannot extrapolate outside of the bounds that you train it in. Think of it like conductivity. If you've ever calibrated a conductivity sensor, you know within a certain range, it's linear, it works, but once you get outside that range, it is completely nonlinear and you can no longer rely on your measurements. So you have designed your data collection, you've maybe stress tested it to get outside of those bounds, you've collected your data. Now let's talk about a couple of aspects of prepping the data. So the first I'm going to talk about are outliers really briefly. The first is we can have statistical outliers, right? So something's a very rare event, but then there's the idea of an outlier that you would want to remove from your data set. And I would encourage you to think very critically about whether you need to actually remove data from the model for machine learning purposes. Because unless you can be sure that whatever erroneous data will never enter your model again, it's important to include it to keep your model robust. So if it is a typo, right, in your lab management system, maybe you implement a new process to ensure that those typos don't get through. If you have a sensor that goes down, maybe you add a qualifier so you're not collecting data during those times. But if those are events that are going to happen in the real world and you're deploying this model, it's important that you know how your model is going to respond in those events. So be careful about picking and choosing what data is included. And then finally, we want to remove irrelevant features. So while we love to think about machine learning as you can throw everything in the kitchen sink in there, the model really performs best when you can remove things that just add noise, because the model will try to fit to the noise. So think about baking a cake. If you had to walk into your pantry and make a cake by pulling out random ingredients, that cake would not only taste bad, but take you a while and have a bunch of extra stuff in it. So it's important to subset down to just what you consider essential, for the most part, ingredients. Here is another example of why we think about that. So if you have lots of variables, but very few observations, like on top, we consider that data wide. But if you have few variables and lots of examples, that's a much stronger model. And there is no hard and fast rule, but you ideally want to go for anywhere from 10 to 100 times the number of observations as you have the number of variables. All right, so you have gotten your data, you've prepped your data, and now we'll talk a little bit about how you do model training. So when you split the data in machine learning, you split it between a training set and a testing set. So in this example, 75% of the data is used for training, 25% is used for testing. So we call that a 75-25 train test split. But what's happening here is I'm training my model, fitting my model parameters, and then measuring the model accuracy on a data set that the model has never seen before, right? So it really tells you how robust your model is. But sometimes you want a little bit better for your training data. So sometimes we'll allow the model to see a subset of that training data called a validation data set. So in this case, I've now taken that chunk of training data and split it so that I train my model, I check the error on the validation data set, and I can make changes to my model. So this is a way that we ensure that we can have the lowest testing error. So this is an example of a 50, 25, 25. Now, the numbers don't mean anything here. I'm not saying this is the best way, but as you parse through the literature, you will see how they did their data split. And that's important to understand. The only thing I'm going to throw out here, and we could do a whole lecture on how to train a machine learning model, is you want to be aware of what's called data leakage. So that is when you have some information in your testing set, right? So something that's supposed to have never been seen by the model before, but somehow it gets into the training data. So think about it like I want to try to estimate what my pH is right now. Well, if I trained on what my pH was an hour ago, there's a chance my model just sees that it's really highly correlated and predicts the value from an hour ago. And the problem with that is that it's not actively using the information I'm providing with it right now, but instead it's just looking at highly correlated data. So if I were to throw it into the wild and there's no data that's highly correlated to it, well, the predictions are really poor. So you'll see this in literature when you see R-squared values of nearly 1 on testing data sets. That's usually a sign something's happened with data leakage. Now, there's a lot of different types of machine learning models. These are just 2 examples of some of the structures. They vary in structure and in size, but what is important is that you experiment with both simple and complex statistical and machine learning models for your data-driven application until, as a research community, we're able to give better guidance on this issue. So put on your experimentalist hat and play around. And then finally, I'm just going to give you a bit on the difference between how machine learning models are fit versus statistical models. So those 100 of 1,000 of model parameters that we talked about, all of those numbers are originally randomly generated. And once the model error is calculated on either the training or validation set, that model parameters are then adjusted based on what are called hyperparameters. So those are the values that you as a user are setting before you fit your model. It's not an actual model parameter, but it tells the model, hey, this is how you update when you notice a model error. And then when we talk about model optimization, that is the adjustment of those internal model parameters themselves until you get an error that doesn't significantly change. And when we talk about model evaluation, the big thing I want to throw out is you're constantly comparing your training error and your testing error. So how is the model fitting on the parameters that it's using, and how is the model fitting on data it's never seen? So this should simulate whatever environment you're expecting it to operate within. And this is important because if you have a really, really low training error and a really, really high testing error, your model is overfit. So that's an example of what's happening on the right. The model is fitting to noise or small correlations within your data that don't represent the general phenomenon you're trying to describe. So seeing a balance between your training and testing error is important for this reason. And then finally, I'm going to touch briefly on how we deploy models. And these are questions you should be asking yourselves in the defining problem step. So understanding this is critical. And where your facility is likely more on the left-hand side of this spectrum here of control strategies, where a lot of facilities are using strict feedback PI controllers. And what we want is to start moving the industry towards the right. But we have to kind of think about what are the existing control constraints and strategies, what are the existing data constraints and strategies, and finding ways to integrate machine learning to move us towards the full data-driven feed-forward strategies. So this is an example of how data can be organized at a facility. And once again, this is going to feed right back into how you do your predictions. So you have on the lower right-hand side there, that's an example of your SCADA system. The SCADA data, which is directly used for control, is usually behind a firewall, which means no information can come in, and that's to ensure that malicious actors can't change what's going on at the SCADA or at the control system level. Now, you can put servers that just have access to SCADA, that don't have access to the internet or elsewhere. That's one place where your machine learning model can live if it is just using SCADA data. Now, for the most part, facilities organize their data not just from SCADA, but from maybe their lab management system, from external sources in a centralized area called a data historian. Now, when you fit a model for machine learning, you are really pulling data from that data historian, from all your disparate sources. And so when you communicate with the historian, you can use on-premise servers or you can use cloud servers. So this could be as easy as spinning up a VM on a facility that is just used for model fitting. And when you have access to the historian, you can pull your data, fit your model, and send it back. And that's a good example if you just want to use it for monitoring or control with a human in the loop. So building a dashboard that can visualize this information, but doesn't need to directly be sent back to SCADA systems. And that is because right now our whole system is outside of the firewalled area. So understand where your data is coming from at your facility, understand the constraints of that, and then you can think about how it can be deployed, whether it is outside your firewall or inside your firewall on a server, either on-premise or in the cloud. So that is a broad overview of some of the important terminology and objectives that we thought about during our process. This presentation is actually available on the Toolkit website, which Joe will now be talking about. So I'm going to pass it off to him.
All right, awesome. Thank you so much, Kate. Yeah, so hopefully everybody at this point is a machine learning expert. But actually, in reality, we kind of understand that these topics are complex. Kate just gave a really, really awesome presentation, but Sometimes people need to sit with this information for a while. You need to go back to a resource after a little bit. Maybe you need to watch a video on 0.5x speed or what have you. And so one of our deliverables for this project was a web-based tool that we call our machine learning toolkit that really aims to kind of jumpstart learning and hopefully even implementation of these machine learning based process control tools. And so I'm putting up on the slides a QR code as well as the link to our project's webpage on the WRRF website. I believe it's also in your portal for this webinar, but it's also printed out in your slides if you have the slides that have been provided for this webinar. But to access the toolkit, you'll go to this project's page on the WRRF website. And then if you scroll down a little bit, there is in the resources section, this link to our machine learning for water process control toolkit. When you click on that, you may have to go through some WRRF logins, but then eventually you should get to our web-based tools homepage that looks like this. And this homepage just kind of gives a brief introduction and overview of what the tool does and who it's for, who are the partners involved in the project. And we kind of specify on this page that this is directed for an audience of process engineers. And we really thought through that audience very hard and felt that process engineers might be the people who are working to drive these machine learning, data-driven based process control strategies. But I don't think we should think of that as like an exclusive audience. I think we worked really hard to make this an accessible tool to folks all around the water industry. If you're an operator who might be interested in possible future directions the industry is going to work towards, or maybe you're working at a utility where they're trying to use some of these data-driven processes, I think this is a good tool for you. If you're a manager who, maybe you've heard about the AI, machine learning buzzwords, you've gone to conferences, you keep seeing it pop up, but you might not be equipped with the vocab to maybe communicate it to stakeholders. Maybe you want to implement this at your utility, but you just, don't know what the next steps are. I think this is a good tool for you. And so we kind of specified a process engineering audience, but I think we aim to make it as accessible as possible. And so on the web page, you'll see there's two tabs in the top right. The first tab is a machine learning overview tab, and it goes through exactly what Kate just kind of took you through. It provides kind of a primer on machine learning, a machine learning 101, you might say. There's a video on there of Kate giving a very similar presentation to what she just did. There is a history of AI and ML, just to give you a background on where we have gone with these technologies and how we apply them in the wastewater and water process engineering fields. There's a primer on vocabulary. So what is regression? What is classification? What's a forecast? What's optimization? It talks about how you can communicate these projects to stakeholders. And then I think one of the most important parts is that it provides additional links to resources. I think we kind of acknowledge that we're not the only tool out there that exists. We hope that this can be a really helpful tool, and we're excited to share it with you all. And we think it is very valuable, but there is a lot of resources out there that can be of use to people when they're looking to implement these sorts of technologies at their utility. And so there's information on each of the steps in the framework that Kate went through, and those links to resources as well. In addition to kind of this primer 101 machine learning overview section, there's also an application examples section in the toolkit. And so each application that was part of this project created almost like a blog style write-up of their application. And so while our final report, is very in-depth and goes into great detail, these are a little bit more higher level, a little bit more accessible write-ups of each application. And so you can click into each of the application examples. You can read about how they defined their problem, how they collected their data, how they prepped their data, trained the model, deployed the model, et cetera, in a little bit more of an accessible format. There's also videos. So each application produced 2 videos, one video just explaining the application itself. So you'll see examples later in this webinar of 3 of the applications. Those presentations and similar ones are presented in the toolkit in form of a video. And then there's also a code walkthrough video. So each application actually provides a link to source code material. And the videos walk you through block by block, step by step of how, with real code, these applications were able to implement the machine learning toolkit framework. We're using a platform called Google Colab, which is essentially just like a Google document, but for code. So it doesn't require any software downloads. It can work on all types of computer environments as long as you have a Google account and an internet connection. And we really feel that that is one of the most easily accessible ways to kind of share this coding information. So even if you've never seen code before, written Python, you just have nowhere to start, it can walk you step by step so that you can go through each step in the process of preparing the data, training your models, and getting results. And so unfortunately, my GIFs didn't work too well, but what that page looks like is just an example of all of the applications, and then you can click on each application image to see those write-ups, the blog style write-ups, video explanations, and code breakdowns. We've also tried to split up each application into a variety of keywords. So maybe you saw in a presentation that the XGBoost model worked really well for a certain type of system, and you want to learn more about XGBoost. You can see which one of our applications maybe used XGBoost, and you can learn more about that specific machine learning algorithm. Or maybe you're interested specifically in nutrient recovery. You can see based on kind of our keywords which applications worked in nutrient recovery or sludge dewatering, things like that. So we're really, really excited to launch this tool. We hope it's a good mix of video content, written content, hands-on tutorials and activities. And we hope that you all can take this tool, share it with your colleagues, and hopefully learn to implement some of these at your own utilities. And it's live, it's launched, and we're happy to accept any feedback as well, or if you find any issues. We want to make this a tool that outlasts this project, so we're really excited to present that all to you. So very brief intro to the toolkit, but like I said, it's live. You have all the information. Please go and check it out. Thanks so much. And I'll turn it over to Jeff Sparks.
Thanks, Joe. Hopefully everybody can hear me okay. Joe, you mind nodding there? Yeah, good. All right, good afternoon, everyone. The work I'm going to describe to you today was completed at the HRSD Nansemond Treatment Plant in Eastern Virginia. In this work, we were attempting, sorry, the slides are moving around. Okay, there we go. In this work, we were attempting to improve ammonia-based aeration control, or ABAC, by incorporating machine learning into the controller. And I know that the slide here mentions AVN and PDNA, and the thought was that any improvements in ABAC would translate to improvements in ammonia versus TIN control or AVN control for mainstream partial denitrification anammox or PDNA. So please keep in mind that for ABAC or AVN or AVTIN, whatever controller you want to highlight, we are simply trying to generate a DO set point to meet our ammonia targets. I don't want that point to get lost as we move through the presentation here. All right, at Nansemond, the existing condition was feedback PI control for ABAC. The problem with feedback only ABAC is that it is less than ideal when the following conditions are present. When the RTD, or the residence time distribution, approaches plug flow, when the influent load dynamics are unpredictable, and when the ammonia sensor is at the end of the tank. And then, of course, if you have all three of these things, then it is a real problem. Okay, so at Nansemond, these first tanks in the biological process, the ones on the left, are physically 6 CSTRs in series, and dye studies confirm that the downstream tank, the downstream aeration tank, which comprises aerobic zones 2 and 3, is made up of 5 CSTRs. So if you combine those two sections of the biological process, you get 11 CSTRs in series. And then the ammonia measurement is there where the dye sampling point was. So it's fairly plug flow. Okay, if the loads were extremely predictable, you could almost program the DO set point according to the clock. But at Nansemond, this was not the case. We see that sometimes the diurnal load curve peak has a shoulder. If you look at that rectangle there to the left, and sometimes it doesn't if you look off to the right, you can see sometimes the valley is close to 0, and then sometimes it's not. You can see the peaks if you look at those two horizontal lines are not consistent, and then of course you have rain events, that big peak right there in the middle, which doesn't resemble any of the peaks for that month shown there on the chart. And so Aman confirms for us in her thesis that there are controller delays when the ammonia sensor is placed in the last aerated zone and the RTD approaches plug flow. And then, in fact, there are lots of things that are going to affect aeration control. And this is probably why Fafana claims in her work that the main optimization factor regarding pDNA is the upstream aeration control, not really the pDNA process itself. Okay, so let's talk about Nansemond for a minute specifically and what's happening at Nansemond. So Nansemond is a full-scale 30 MGD design flow facility. The biological process is a single sludge 5-stage Bardenfo. The aerobic zone of the Bardenfo is shown there in the middle where you see those brown bubbles. The aerobic zone is split up into 3 zones, zone 1, zone 2, and zone 3, and then you can see zone 1 off to the left there grayed out because zone 1 was not the focus of this work. After zone 1, the flow enters a common aerated channel you see there, and then the flow is redistributed to zones 2 and 3. Zones 2 and 3 were the primary focus of this work. After zones 2 and 3, flow moves into the second stage anoxic zones where we feed methanol for denitrification, and work is currently underway to convert the first 1/3 of those second stage anoxic zones to pDNA IFAS. And that's shown in red to show that that's proposed for the facility. And then the eventual conversion of pDNA to pDNA means that we'll eventually move from ABAC, to either ABN or ABTIN instead of ABAC in the future. So, okay, so let's focus on ABAC in aerobic zones 2 and 3. So by focusing on those controllers off to the right. So the baseline control, like I said, it was a feedback PI controller that looked at the ammonia leaving zone 3, where that yellow star is, producing a common DO set point for aerobic zones 2 and 3. And then there's the DO set point that comes from that first ammonia controller and goes to a DO controller that produces an aeration control valve position. So you have the combination of the ammonia controller on top and the DO controller on the bottom, and those two things together produce the ABAC controller in its entirety. Okay, so the foundation for the controller upgrade, so I just showed you sort of the baseline, was the digital twin at the Nansemond treatment plant. And you can see here the digital twin is pictured in Sumo by Dynamita if you look off to the right there in that white box. Okay, all right. So from the digital twin, or the DT as I'm going to call it, we were able to soft sense some nitrifier specific parameters like the nitrifier concentration and the growth rate we were also able to calculate the mechanistic model error, which is simply the modeled ammonia minus the observed ammonia, if you look up over there to the top right. And then if you look kind of under those two, so 2A and 2B, you can see those parameters sort of moving down the data pipeline as I've illustrated it here. So the nitrifier population, the growth rate, and the mechanistic model error. Now, since we have a history now of the mechanistic model error, because we're constantly tracking what that is, we can use that history and use time series forecasting models to generate error forecasts. And then we use two types of models, or what we call forecasting engines. One we call the MEF, which is the mechanistic error forecasting engine, and one we call the WRRF, which is the residual oscillation forecasting engine. And the MEF does just what it sounds like, and it forecasts the digital twin error, and we call that error MEF. And after applying the MEF, we noticed that the residuals still had some periodicity in them, and the WRRF is what captures that periodicity. So it's like two data-driven models on top of each other, combined with this mechanistic model that is the digital twin. So it gives you this hybrid model. Now, ultimately, the nitrifier parameters and the error forecasts are transmitted to the control system, which you can see there at the bottom of the slide. Okay, so I'm going to show you some results here on this slide. Now, these are modeling results, not controller results, hybrid model results. The gray scatter points that you see there are the actual ammonia observations, and you can see we were experiencing a bit of an upset at this time, registering some pretty high ammonia concentrations, peaking at almost 6 milligrams per liter. Now, the timeframes for these two charts are effectively the same, the left and the right. So the DT, or the mechanistic model in this case, said the concentrations should have been where you see that solid gray line there kind of towards the bottom. So not doing super well with the digital twin or the mechanistic model forecast for ammonia, but using machine learning models, we corrected for that error from the mechanistic model. And then the MEF said the ammonia should be where that dark blue line is. So you can see getting pretty close there to the ammonia observations. And as I said, there was still some periodicity there in those residuals, which you can kind of almost see if you look at the difference between the observations and the MEF. And the WRRF captured that and cleaned it up. I like to say that the WRRF bats clean up. All right, so you can look at the text box at the bottom there for how the model errors improved with the addition of each model. Okay, so on this slide, I'm going to talk about, so we talked about the models, right? And we talked about the digital twin, but we haven't talked about really the new controller architectures and what they look like. So that's what I'm going to spend the next couple minutes talking about. So on this slide here, you can see what we did for zone 1 and the modifications we made there. And that was actually pretty simple. We just had the DO set point follow the influent ammonia load, such that when the load was high, we had 2 milligrams per liter of DO in zone 1. And when the load was low, we had a DO of 0.1. So you can see the DO concentrations there on the bottom and then the load there on the top. So in zone 2, we used a feed-forward feedback controller. We installed an ammonia sensor in that common aerated channel that you see there highlighted with the blue star. So that's where the sensor was placed. And we used the same ammonia analyzer we've always used for feedback ABAC, where the yellow star is for the feedback component. Here is how the DO set point was calculated for zone 2. And so you can see some of the stuff that I've been talking about in this calculation. So you got the feedback correction there, which is in that dark blue. You can see we have the growth rate and the nitrifier concentration there in dark green from the digital twin. And we have our two error forecasts, our MEF and our WRRF there on the very bottom of that calculation. And then you have the ammonia measurement there in the light blue, that NHX 0. And I do want to make the point that the feedback controller for this feed-forward feedback controller, so the feedback component anyway, was tuned very slowly. All right, and then finally, we made zone 3 this sort of like trimming or polishing zone with a very fast controller, which makes a lot of sense because that's right where the ammonia measurement is, and we don't have a lot of delays there. Okay, so now let's look at some of the controller results where you see those light gray scatter points. So those are the ammonia concentrations measured at the aeration tank 6. Now, aeration tank 6 did not receive the advanced controller here, just used the baseline controller for the duration of the study. Now, the solid black line in the middle is the ammonia set point set at 1.5 milligrams per liter. All right, so let's focus on the chart to the left first. Those gray scatter points with the blue outline, so kind of on top of the light gray ones, those are the ammonia concentrations in aeration tank 4 before we deployed advanced control in aeration tank 4. So tank 4 is the one that got that new advanced controller that I described to you. But before it got that advanced control, you can see it pretty much has the same performance as aeration tank 6. And then boom, we give it the advanced controller. Now we see those peaks immediately come down, but we don't see the ammonia concentrations really centered on the set point. That's because we hadn't added the feedback component to the feed-forward feedback controller yet. We did that where you see that solid vertical blue line, and all of a sudden you can see now our ammonia concentrations are centered on the set point coming out of tank 4, with some reduced peaks and maybe some valleys that don't dip as low as aeration tank 6, which is sort of like our control here. Now, we had some glitches with the control system during this whole experiment. We had to abandon the advanced control in aeration tank 4. And then in the meantime, when we did that, we did some tuning for the feedback controller and the feed-forward feedback for zone 2 and for zone 3. And then when we re-engaged the controller for aeration tank 4, we got the performance you see there on the right. So that's the advanced control now with tuning. And if you want to look up to the top right corner, you can see the various results for aeration tank 6, which was the control, the advanced control before tuning and after tuning. And we were very pleased with these results, as you can imagine. So what did we learn? Well, we learned that the DT itself, the digital twin by itself, is not perfect, likely due to some physical disparities from tank to tank as you look at these various tanks in parallel. And we also discovered that the digital twin's performance can be much improved. I mean, if we're just talking about the digital twin with the addition of the MEF, just through data-driven correction. And then we also learned that adding parameters to these data-driven models to do this mechanistic correction really didn't improve performance all that much, and it wasn't worth the additional parameters and complexing the models to do that. And so it worked well enough that we want to take what we learned from aeration tank 4 and expand that philosophy to the whole planet, Nancy. So I am finished up here. I'm going to hand it over to the next presenter. Thank you.
All righty. Well, next application is going to be application number 4. It's going to be discussing, phosphorus recovery. My name is Rudy Maltos. I'm a process engineer at Metro Water Recovery. This is where this research was conducted. This is where we actually collected all of this data itself. The Robert W. High Treatment Facility. It's located right outside of Denver, Colorado. Here in this figure, you can see we have a north and secondary process, and the whole facility is wrapped around by the South Platte River where we discharge it into. And so, we're rated for 220 MGD. On average, we're seeing around 130 MGD into the facility. But for today's discussion, we're going to focus on the solids handling, specifically that phosphorus component right in the middle of the facility. Okay. The big driver here that we have is, of course, going to be regulatory. Currently we're under Regulation 85 at Metro. Total phosphorus limit is 1.0 milligrams per liter, and that started in the year 2022. We currently target a 0.7. That's because we have a voluntary incentive program. If we are able to achieve that 0.7, then we're going to have some more time to achieve the next regulation that's coming down the pipe, which is going to be Reg 31. And that's going to be a 0.1 milligram per liter total phosphorus, so super, super low phosphorus concentrations. And that's just due to us discharging into that South Platte River directly. So how do you actually get to such low concentrations? Well, it starts off all the way back in 2012 for us when we implemented enhanced biological phosphorus removal. So with phosphorus removal, you need to have an anaerobic zone. So we converted our MLE process, just having anoxic aerobic volume. We added a side stream anaerobic zone. This allowed our phosphorus accumulating organisms to take up that phosphorus, leaving low effluent phosphorus in our final effluent. And then that just simply diverted, though, that phosphorus stream into our digesters. And that was a problem because with that diversion of phosphorus into the digesters, you're going to get precipitation of struvite, and then also you're going to get a recycle stream of phosphorus going back into that secondary process. So it didn't really resolve the problem completely here. So what did we do? And before just getting into the solution itself, this is just some of the consequences of enhanced biological phosphorus removal. I mean, the pipe diameter here, you can see cut in half. That precipitation strurite being a combination of magnesium, ammonia, and of course, orthophosphate being present. So a huge problem for operations and maintenance having to deal with this every single week. So what was the solution that we settled on? We decided to move forward with the implementation of the largest MACPREX reactor. As you can see now, we have this reactor here. After the anaerobic digestion process, we're bringing in that digester effluent. We are giving ourselves some HRT. We're increasing the pH by stripping CO2, and we're adding magnesium chloride, which is going to get this precipitation to happen very quickly. Large crystals will settle out to the bottom of the reactor, and then the rest of that soluble phosphorus will go from that soluble state into a particulate state, which we can then recover in the dewatering phase of things. So you can kind of see that here. So we're able to kind of change those streams of phosphorus, and we're able to now send back a low phosphorus stream into our secondary process. Here's the reactor itself. Again, the largest in the world. It's not always the best being the largest, so it has its own challenges, which we can discuss at some later date. And here's a MACPREX process flow diagram. So again, we're taking that sludge, the digester effluent. It's a completely mixed reactor going into the MACPREX reactor. Our control variables, the ones that we're going to be mentioning today, are going to be the blower. This is what's going to be changing the pH as you strip CO2 from the reactor. And the other control variable is going to be that MAC chloride dosing. So the amount of magnesium chloride is going to be dependent on the amount of OP going into the reactor. So it's really important to track how much orthophosphorus is going into this reactor. And then with that, we're going to then go into the MACPREX effluent and then finally dewatering. So what makes application really unique compared to all the other applications within this study is that we're combining a lot of online data with the lab data. And so, of course, online data is helpful discussing about flows and pHs and set points. That's great. But it doesn't really tell us anything about the performance of the reactor. With that, we have to really rely on the data that we're collecting from the lab. So this is going to be TSS, orthophosphate, total phosphorus. We're going to be running ICP to look at what that magnesium is doing. And so we're really blending both of these streams together to kind of hopefully understand what's going on within the reactor itself. Okay. And so with that, the current challenges is that, like I mentioned earlier, OP, understanding the amount of the OP concentration going into the reactor is very important so we can dose the correct amount of magnesium. But it's a very difficult matrix to kind of sample in. So we only do this once or twice a week. So this means that this dosage of MAC chloride isn't very dynamic. It's very static. You can, of course, just add more magnesium chloride, more than you think that you would need, but that also leads to a problem downstream. You actually start to precipitate strurite in the centrate system, which leads you back to square one, right? So you don't want to do that. But if you don't dose enough MAC chloride, then you're not going to get the OP transformation that you need. As I mentioned before, it's a really difficult matrix. So there is no OP analyzer that can go into digester effluent. So this goes into the proposed solution that Joe's going to be talking about next, investigating statistical and machine learning methods to predict daily OP levels so we can kind of adjust that MAC chloride set point. And then that machine learning model is going to be able to kind of give us a recommended MAC chloride set point that we can ensure that we're meeting the effluent OP targets of the reactor. And with that, I gave you guys some background on, the process. Joe's going to go into now the details of the model development.
Awesome. Thank you, Rudy. Yeah. So like Rudy said, this was a unique application because of the amount of laboratory and online sensor data that we were mixing in our data set. There's a lot of cool data preparation techniques that we use that I won't spend too much time on, but I would recommend checking out the toolkit to kind of get insights on that. But one of the things I will talk about kind of on the data prep side is this variable selection piece. And Kate mentioned it at the beginning of the webinar in her talk. But variable selection, it can be a really helpful tool because if we kind of look at this dartboard almost, and if all the dots are just all the variables that we're monitoring, it's likely that we're going to have some variables that just don't add to any of the predictive ability of the model, and so they're useless. And so we can kind of remove them from our models. There's also likely some variables or features that provide a similar or the same amount of information to the models as other variables or features. And so we can also get rid of those redundant features. What we're targeting kind of is this minimal optimal subset of relevant variables to help us kind of optimize our data collection process and maybe ease maintenance and data collection requirements. as well as improve our model fitting. So if there's a lot of variables, you can have noise that can cause overfitting in your models and possibly decrease the accuracy of your models as well. And so we investigated a handful of variable selection techniques, and the ones that I'm showing here involve using Spearman's correlation coefficient, principal component analysis, and then a method called the maximum relevancy minimum redundancy method, or MRMR. And so we used a bunch of these variable selection techniques to try and see what is the optimal number of variables to keep in our models. We also compared a variety of different kind of more simpler statistical and maybe more complex machine learning models to each other to predict, like Rudy said, the influent orthophosphate coming into the reactor, the effluent orthophosphate, and the amount of orthophosphate that was being removed by the reactor. So in these plots, I'm showing error versus the number of features kept, and then the different lines of the different types of models that we fit and trained and tested. And so what we can kind of see in these results is that we can actually reduce the number of variables that we track without really significantly impacting the errors. And so here, lower is better. And you can kind of see by the highlighted square there that, you know, the difference in the error between 10 variables kept and 80 variables kept really isn't that high. And so that kind of indicates to us that we really don't need to be monitoring all the variables that we had in our data set. Additionally, we see model improvement over our kind of baseline mean model. So it kind of justifies in our head that, yeah, hey, maybe data-driven modeling or machine learning modeling can actually be a beneficial tool in this case, because it's actually improving upon, you know, an existing use case. However, you know, just because there is an improvement doesn't mean it works in all cases. And so what I'm showing here on the right is a plot of the model outputted predictions versus the actual measured values. And you kind of see that at really high concentrations of orthophosphate, the model predictions kind of break down. They're not as accurate. And the reason for that is in our initial monitoring data set, we just didn't have a lot of days where there were high concentrations of OP. And so because our models, when we were training them, didn't see a lot of data where the orthophosphate concentration was high, it turns out they couldn't really extrapolate and predict very well at those high OP concentrations. So how can we turn these predictive models into magnesium chloride set point adjustments? Well, we can do what Metro's doing now, where they just take the OP measurement and then they adjust the set point based on that. We can say, okay, let's use our influent OP predictions to then adjust the set point based on that. But when we do that, if the kind of green diagonal line is maybe our ideal set point adjustment, we kind of see that we get these really sporadic recommendations for magnesium chloride set point adjustments. And so maybe using influent predictions isn't really the best tool. If we use effluent predictions and maybe do more of a feedback loop, we can kind of see that our magnesium chloride set point adjustment recommendations fit a little bit more neatly along kind of this ideal diagonal line. So we deployed both our predictive model, or all of our predictive models, and our magnesium chloride set point adjustment model at Metro as a digital shadow. So these aren't actively changing set points, but they're more a decision, a recommendation tool to operators. So we deployed them as a digital shadow using GitHub and Anaconda and some tools. And I'm showing some results from the deployment. And we see a similar story as we saw in training, where you know, our models are generally accurate at maybe the low and middle concentrations of OP, where we see kind of the majority of data. But at those really high concentrations of OP, our model tends to break down, which is really important when you're trying to implement these as maybe more of an automated system or as a decision kind of recommendation system. When we did a TEA and LCA, we did see that based on our set point adjustments, we were able to see a 7% reduction in total OPEX of the process, and also an 8% reduction in certain LCA impact categories. So with additional tuning, we think that this can be a really successful model for the MagPrex system. Just real quick, some general takeaways and conclusions. Utilities have really dynamic data environments. You're going to have sampling locations that might change, or infrastructure upgrades. And so you need to really understand, how do I retrain my models in the face of those changes? Additionally, if you're working with outside consultants or academics, you know, understanding your cybersecurity protocols and how you can give access to code and data is really, really important, and can slow down project implementation. Machine learning models aren't always the most accurate, and you need to know in what situations to maybe not rely on them, or maybe they're not accurate, in our case, at really high OP concentrations. And also, we see that there may be some direct cost savings in this project, but there's also some indirect cost savings that can make this project even more worthwhile, including reduced maintenance, reduced data collection, and just overall improved operational efficiency. So a lot of work is still going on in this system, and we're excited with the results we have and the results moving forward. And so with that, I'll hand it off to Nam to talk about the last case study for the event.
Thank you, Joe. Hello, I'm Nam. Today, I will walk you through the holistic solid optimization at DC water. Our model workflow, we follow exactly the same with what Kate and Joe mentioned before. The first problem right now, when your total solid higher than 2%, the time that we cannot rely on the TS rub, because the time that you go and clean your TS rub will be more than the time you just go and collect the sample and do the lab measurement by yourself. That's the reason why at Blue Plant, our operator, they have to go to the field, they collect this sample to do the lab master TS around 5 to 6 times a day to make decision on dilution water in biosolids treatment. This is the overview of the biosolids treatment at Blue Plant. So we have to make decision on dilution water at 3 locations. The first location is bubble feed line, so that TSP feed, we target the TS of 16.5%. The next location is digestive feed line after TSP system, we target 10.5% of TS. And after digestion, so we target the TS of 3.5% before we send the lush to final dewatering. The main driver here can be automate, so to reduce the labor intensive, as well as achieve more reliable performance of the biosolids treatment. Get data. My team has been using acoustic sensor. You can see in the picture. Acoustic sensor has been used in the other sector for particle size distribution, bubble concentration. And the main principle of acoustic sensor will be capture the viscosity. When your TS change, the viscosity change, and then the frequency and signal from captured from acoustic sensor will change. The advantage of acoustic signal will be you can mount it outside. You don't need to clean your acoustic sensor, as well as we can install in a different location. Next, this is an example of how an acoustic signal look like. This is amplitude versus frequency. This is sound wave. We can capture around 6,000 of frequency versus amplitude. And when we transfer from time domain to frequency domain, acoustic sensor can capture a wide range of frequency from around 12 to 100 hertz. You can see. And of course, when the TF change, viscosity change, the frequency will change. Next. Our team has been, used 2 years of training data at 3 locations I mentioned before, the final dewatering feed, digester feed, and bubble feed. We capture the lab master TS together with acoustic signal, and we develop a TS prediction model, and we calculate the root mean square error. If you look at the first 3 graphs from the left side, if we just look at the root mean square error, the root mean square error less than 1, but less than 1, it seems good. Is that a go or no go? And then we want to quantify the true prediction power of developed TS model. So we just develop a baseline model. What do we do with the baseline model? We just guess in the mean value on the time. For example, if we look into the digester feed line, we just assume the TS of the digester feed line is 10.5% on the time and calculate the root mean square. And then we consider that as a baseline model. And when we compare between the baseline model or the mean model versus the developed TS model based on the root mean square, the model developed was not better than the guess in the mean value. Why is it? Because if you look into the graph on the right-hand side, the training data, the TS for the training data had no variability at all. You can see the training data for the digester feed line is just around 10.5%, just small variation, the same for dewatering, the same for bubble feed line. What does it mean? Why? Because our operator they are doing a very good job there. And so, however, when we develop this model, we want to capture the extreme event. So that's the purpose. What do we do? So we know that's the challenge. We don't have the variation of the data. So we One step back, we run a by-loss scale. You can see on the graph on the left-hand side, we do a by-loss scale. If you look into graph A, you can see that right now we can achieve a wider range of the TS from around 5 to 14% to evaluate our model development again. And then if you look at graph B or graph C, it will clearly that with a wider range of the TS for training data, the frequency from acoustic sensor and the model working really well. That's the reason why that's a goal decision for us to go back to the full scale to get more data variability for training model. We focus on digester feed line. If you look at the graph on the left-hand side, that's the normal distribution of the TS. It's just around like 9, 10, or 11%. Again, our operator, they do an excellent job there. And then we did a lot of experimental sampling campaign. So we work with operator and RAS engineer to do different dilution to get a better training data from. Right now, I can get the TS for the training data from around 5 to 14% for my model development for just the feed line only. Let's see how the model works. We train the model, and right now we evaluate the model. We look at the very simple model, linear regression, to a complex model like attribute or random forest. And right now, when you compare, when you look at graph B, the developed model works much better than the baseline model, just guessing the mean value. I want to give a note here. We were able to do experimental campaign to get a wider range of TS for digester feed line only. We couldn't do it for final dewatering because if we do that, we will mess up a whole final dewatering facility as well. We couldn't do it with proper feed line. Deploy model. After that, that will go for us to go and deploy the model. So currently we deploy the TS prediction model at digester 3. Digester number 1 feed line, as well as recycle loop. I want to give a note here. The TS model was developed based on the training data we captured from digester number 3. Digester number 1 is the new location, new sensor box, as well as recycle loop. Again, you can see digester, again, recycle loop. This is a new location outside the building with different noise background. In addition to that, the bioside are bigger and different to compare with just the fit 3-in-1. In each sensor box, we have Raspberry Pi. We capture the acoustic signal. The Raspberry Pi will connect to DC water network, and we send to central computer to predict the TS. And then central computer will send to the BSS system, so operator can get hourly online predicted TS from BSS system. Let's see how the validation look like. So we have the digester 3, 1, and recycle loop. The x-axis is the lab method TS, and the y-axis is the model predicted TS. Sorry, the font is quite small. But so far, those 3 locations, the TS model works quite well. Especially we can capture some extreme events, so like really high TS or super slow TS, that from the data. This is a goal decision for us. Right now, we're working to transfer the current model development to roster engineer and operator, so they can access to the BSS system. So they look at the online predicted TS to make decision for dilution for the dilution water. So take home message so far from our case study. What do we learn so far? The first point from our case study, we need to quantify the true prediction power of your data-driven model development. We can consider the baseline model, or in our case, we're using the predicting the mean model, but it depends on each application. Second thing, the data variation is really important for data-driven model development, because especially when you use full-scale data, because operator, they do their job and they enhance the system really well. And with the data-driven model, we want to capture some extreme event. And the last point, we need to evaluate the local applicability of the model development. For example, right now, in our case study, it's what a blue plan. So how easy for us to transfer to the other facility? What is the effort for us to train and to tune the model? And so some of the question. That's one from me. Thank you, everyone. And now we get back to Nancy and Jeff for Q&A session.
Thank you, Nam. And now I'd like to ask all of our speakers if they'd be willing to turn on their video cameras, and we'll have a discussion and Q&A session with all of our presenters. Keep the questions coming in, by the way, and we do have a fair number of questions that have come in already. And Dr. Nancy Love, professor at University of Michigan, will be co-facilitating our Q&A session along with me. And Nancy, I don't know if you want to kick us off.
Yeah, I thought I would, and I think that's thanks everybody for your presentations. First of all, I'm really glad we're able to answer the questions that have come in, and some of the questions were answered in the portal, but we're going to go ahead and review a few of those here. I'm going to start with the one about security and the access to data retention. If you're concerned about cloud usage, about data retention by outside sources. So some municipalities are sensitive to use of the cloud to store data. Jeff, you gave an answer. Rudy, I was going to ask you to also comment maybe in NAM from a standpoint of your utilities, because it may be different across different utilities. Jeff, you want to say what you said?
Oh, Nancy, I was going to make one note. I don't know that the audience can see all the questions that come in. It's just
perfect. Okay, well, it's good.
Yeah, and they may not be able to see the answers. So
okay, good. Well, then we're going to go over them anyway. There you go. So Jeff, why don't you go ahead and say what you had to say, and then Rudy and Nam, I'll ask you to pitch in as well about that.
Yeah, I just wanted to point out that there is an architecture that doesn't require use of the cloud, and so that's what we did in this case at HRSD. Is we did everything on-prem on a separate server, hardwired to the distributed control system, no access to the internet. So it wasn't an issue for us.
Yeah. Rudy?
Yes. Jeff is kind of a unique situation because, Jeff is a process engineer and also machine learning, data science kind of guru. I guess I'm more of a traditional process engineer where I have a light understanding of a lot of these things. But for me, I had to really rely on, our IT and then Kate and Joe interacting with them to kind of see what that would be the best place. So for the most part, we housed a lot of that on site, but it took some time to kind of get that established. Josh Goldman is another process engineer that had to kind of work to get that kind of developed. But maybe Joe and Kate can kind of speak to you a little bit how difficult it was for somebody on the outside to actually get access to the inside of the utility.
Yeah, I can hop in there. I had to have Rudy and Josh download data from their data historian. I had to give them the specific, what is it exactly that I want, what time frame, what type of data, and then we had to send it. They had to send it to me, email it to me. Then I would be like, oh wait, that wasn't right. I need something else. Then they had to repull data from the data historian, and then so that's a big issue, just data access in general. I didn't have direct access to their data historian. Code-wise, what we were able to do is I was able to basically test on offline data with my code, transfer the code to them through GitHub, and they were able to set up their own computer system running the code so that internally on premises, so they were able to pull the data from the data historian directly and then output the model back to the data historian.
Yeah, and the model output then, I would give those outputs to Joe so that he can recalibrate as needed, but then we would also just have to manually put those in if he decided that it was the correct prediction. So that's how we were able to kind of move that forward. So I guess it's what we call the digital shadow, right? So it's not like the full implementation, right? But that's how we first wanted to kind of move this forward.
Nam, anything to add to that is different?
Yeah, yes, Nancy. For the case study of DC Water, so this is in-house development. So we just connect to the DC Water network, and then we send a signal to the business system. So we had no issue with the cybersecurity issue.
Okay, and so what I'm hearing is that Yeah, there's the development of the algorithm, and in some cases there's a lot of manual interaction with the utility, and then even during implementation, if you want the model to learn, there may be the manual. That's at least the way that our team was working with this. And Kate or anybody else have any final comments about how you see this changing in the future, or do you think that's kind of where we are because of cybersecurity issues?
I think that for critical control points, everything will still need to live on-prem in a server that is firewalled without internet access. That's just how we are currently set up. I think as we talk about other decision support tools, exposing a subset of data through, for example, Microsoft Azure, through secure portals, I think is possible. But once again, I think it's important to emphasize all of this this was a new skill, a new technology that was being implemented for the first time at our facilities. So you're kind of learning from our learning experiences, and we're not saying this is the right way to do it, but hopefully this is how you can start having conversations. And I think the simple answer is start just trying to get something on-prem, and we can talk about getting it to the cloud later on as it becomes essential for you to have more frequent collaboration with consultants that were helping you maintain these models, or academics, or if you find that your computational needs are so great that your on-premise servers can't supply those. So those would be the two instances where cloud, I think, would be essential.
Okay, thanks. We've got, I think, is it 5 minutes left, Jeff? So we've got a lot of great questions. And I know that there's an ability for us to get back to people with those questions if we don't have time today. I'm gonna go to, there was a question about AI and use of AI, and the impression, we know that has a big energy cost associated with it. The question is, what is this going to do in terms of kind of the overall real energy associated with bringing AI into operations? Kate, do you want to take that quickly? Here's a good question.
Yeah. As I mentioned before, unfortunately, water data is relatively small potatoes. So we are not talking about billions of data points. We are not talking about retraining and re-optimizing a model with billions of data points. The majority, actually, I can say this with confidence, all of the models developed for this work were done on desktop units with nothing crazy or spicy, relating to computational power. So the greenhouse gas emissions that, once again, we did not quantify this, so I think it's a great research question, but I would say that this is not on the scale where that would have any impact relative to the greenhouse gas emissions we'd be trying to mitigate facility-wide.
Okay, thanks. Jeff, if you see any questions that you want to get out, go ahead. I do see one that I wanted to ask Nam, because I know that for your application, there was consideration of using digital or video-based data at one point. I think there was a decision not to continue with that, not that it's not an option, but can you comment? There's a question of what are the limitations of ML or AI in its application for video review? Some utilities use a video-based feed to, evaluate a sewer line or some aspect of their process. I know that I think it's possible. You want to make any final comments on that?
Thank you, Nancy. Great question. I think in this application, for this study, we focus on using acoustic signal only. For the video and image processing, my team is still working on that. I think we keep the team updated in coming month or years. Yeah. So it's not the target for this application. So right now, this current case study, acoustic signal only.
Great. Jeff, we've got 2 minutes.
All right. Do we have time for maybe one more question and then wrap up?
Yeah. Let's see. Rainfall. I think there was a question about, the variability coming into plans. The one person asked rainfall. There were a couple of questions along these lines. It seems to me that coupling those models with the treatment process model is possible. Kate, do you want to make a comment on that?
Yeah, so while you can incorporate rainfall forecasts into models, it is important to remember that the forecast is an estimation. And so trying to get the historical forecast it is a difficult data point to get in the first place, because otherwise you're feeding in the actual rainfall, not what was forecasted by, if I could be right 50% of the time, like a meteorologist, that'd be fantastic. So it's actually a greater data technical challenge than you would think, but it is widely that's an active area of research. I know a lot of folks are working on incorporating rainfall data into their models.
Thank you. And great questions, everyone. We'll be getting back to everybody. Go ahead, Jeff.
Yeah, thank you. I think we're about at time. So any questions that we weren't able to get to in the webcast today verbally, we'll follow up with some written responses to those to ask those questions. So thank you for all for asking the questions. Just wanted to share this acknowledgement and disclaimer. Thanks to U.S. Department of Energy, Office of Energy and Efficiency and Renewable Energy for helping to support this research project. And also would like to thank all of you. This concludes our webcast. Thank you for participating. Special thanks to all of our speakers today, Kate, Joe, Jeff Sparks, Rudy, Tom, and Nancy. And thanks to all of you for participating, and have a great rest of your day.